Welcome to This Explainer. Today, I'm stepping right into the role of your mentor. Together, we're going to walk through the absolute critical safety protocols, the exact shop math formulas, and the specific machine setups you need to master to pass your machining NC2 assessment. If you want to walk onto that shop floor with total, unshakable confidence, well, you're in exactly the right place.
All right, here is our game plan for today. We're going to cover surviving automatic red flags, drawings, tolerances, and measurement, shop math without calculators, flawless lathe and mill setups, and finally, handling hazards and malfunctions. Let's dive right in.
Section 1. Surviving automatic red flags.
Listen, before you even think about cutting a single chip of metal, you have to know exactly what will get you instantly kicked out of the assessment room. Under Philippine OSH law, a safety violation is an automatic, not yet competent. It literally doesn't matter how flawlessly you machine your final part. If you fire up a machine without the assessor's explicit go-ahead, if you yank off a machine guard just so you can see better, or if you forget your safety glasses, you fail, period. And hey, treat housekeeping as part of your active demonstration too. Wipe up that oil and clear those chips as you go, because assessors are scoring your consistent, ongoing safety habits, not just what your workstation looks like at the very end.
Okay, moving on to Section 2. Drawings, tolerances, and measurement.
Let's talk about the blueprint phase, because misreading an engineering drawing is the fastest possible way to produce an out-of-spec part. Assessors absolutely love testing your understanding of technical callouts. When they ask you to define tolerance during the oral questioning, they don't want some vague textbook concept. They want the numbers. They want you to prove you understand acceptable limits in the real world. So, if a drawing says 20 millimeters plus or minus 0.05, you need to confidently look at them and state that anything from 19.95 to 20.05 millimeters is good to go. If it falls outside that band, even if it looks or feels super close, it's a rejected part. Now, to measure those tight tolerances, you need the instrument selection matrix. Choosing the right tool based on the drawing's required precision is an absolute must. Rough length? Sure, steel rule is fine. But for precise work, you have to grab the right gauge. And a quick mentor note for you here. Part of your overall competency is how you actually handle these tools. You've got to store them safely, keep them pristine, and verify their calibration before you take a single measurement. A perfectly machined part that gets measured wrong just because of a dirty or uncalibrated tool, that's going to read as a defect on your score sheet.
So how do you choose between the two most common precision tools? Well, a vernier caliper is your Swiss Army knife. It's incredibly versatile for external, internal, and depth measurements, and gives you an accuracy of about 0.02 millimeters. But, and this is crucial, whenever your drawing's tolerance calls for better precision than 0.02 millimeters on an outside diameter, you have to step up, put down the caliper, and reach for that micrometer.
Here is a massive pro tip to use during your assessment. Literally speak your measurements out loud as you take them. Say 28.12 millimeters. Why? Well, it serves two huge purposes. First, it completely prevents those common, silly mental transcription errors as your eyes move from the part to the tool and back to the drawing. Second, assessors will frequently ask you to read an instrument cold, with no part attached at all, just to check your raw technique. Vocalizing your reading visibly and audibly signals that you know exactly what you're doing.
Section 3. Shop math without calculators.
It is time to step into the mental sandbox for the most common oral questioning topic, shop computations. But before we get into complex formulas, I want you to permanently etch this number into your brain, 25.4. There are exactly 25.4 millimeters in 1 inch. Assessors are going to test your unit conversion. And mixing up imperial and metric units during your exam is a super frequent, yet entirely preventable way to fail. Always convert your numbers to match before you plug anything into a formula.
Let's do a really focused tutorial on solving the spindle speed formula entirely in your head, no calculator needed. First, memorize the rearranged core formula. N equals 1,000 times your cutting speed divided by pi times your diameter. Okay, let's say the assessor hands you a 32 millimeter piece of mild steel. Your cutting speed is roughly 30. Step 3, multiply 1,000 by 30 in your head. That's 30,000. Easy. Now the bottom, pi is roughly 3, and 3 times 32 is roughly 100. So what's 30,000 divided by 100? It's 300. You calculate roughly 298 RPM mentally, so you just turn to the assessor and confidently say you'll set the nearest gear to 300 RPM. Boom. Step by step, completely without a calculator.
Moving right along to Section 4, flawless lathe and mill setups.
Okay, math is done. Let's transition over to the iron and steel and walk through how to set up your machines safely. Now pay attention here. Assessors watch the first 2 minutes of your lathe setup incredibly closely. Before you cut a single chip, you're being judged. You absolutely must inspect the machine and verify that the emergency stop is fully accessible. When you mount your tool, you have to line that tip exactly to the spindle centerline height. And please, keep your tool overhang short. If you have excessive overhang or the wrong tool height, that's a setup error that's going to ripple out and ruin every single cut you make after that. If there is one golden rule in machining, it's this right here. Always take your first cut light. Stop the machine and verify your actual size. If you measure it and your part is slightly oversized, great. You just take another pass. It's a super easy recovery. But if you cut a shaft undersize, that part is completely scrapped, and honestly, you will likely fail that entire competency unit on the spot. Now, over on the milling machine, your setup demands just as much discipline. Secure your workpiece and always check its squareness with a parallel bar. Mount your cutter and absolutely confirm the rotation direction. Getting the rotation wrong is an immediate, hard safety stop. And here's another tip. When you set your work 0 on the X, Y, and Z axes, narrate your process out loud to the room. Say, touching off X here, 0 set. This proves to the assessor that you have a deliberate, repeatable method and you aren't just making a lucky guess.
You are practically guaranteed to be asked about the difference between these two techniques during oral questioning. Conventional milling feeds against the cutter's rotation, and it is absolutely the safer default on manual machines. Climb milling, on the other hand, feeds with the rotation. While it definitely yields a much better surface finish, using climb milling on a manual machine that doesn't have a backlash eliminator, no way. That is a major safety hazard, because the cutter can aggressively grab the workpiece and literally rip it right out of the vise.
Finally, Section 5, handling hazards and malfunctions. Let's simulate the situational scenarios round to see how you handle sudden contingencies on the shop floor. Imagine this. You're right in the middle of a cut on the lathe, and suddenly the part starts chattering really loudly. What is your very first move? Assessors want to know if your instinct is to bravely push through or to stop and problem solve. Your answer needs to be instant. Back the tool out and stop the feed immediately. Never just let it run through. Chatter is usually caused by having too much tool overhang, a loose workpiece, or just having the wrong speed and feed combo. Pushing through chatter is a critical error because you risk snapping your cutting tool and completely destroying the part's tolerance. Fix the setup first, then resume.
Let's talk about bench work for a second. Tapping is widely known as the most failure-prone bench operation. Why? Because a crooked thread simply cannot be corrected. Once it's angled, it's done. To prevent this, always sight your tap against a square from 2 different positions 90 degrees apart before you make your first full turn. Checking from just one side can easily hide a bad angle. If it does start off square, stop immediately, back it out, and report it. Look, mistakes happen to everyone. When you inevitably make a measurement error or cut a little bit out of tolerance during the assessment, your reaction in that exact moment will determine whether you fail the competency unit completely or just take a minor point deduction. The only right answer here is complete honesty. Tell the assessors straight up what happened and exactly what your measurement reading is. Trying to hide a defect is infinitely worse than just making an honest mistake. In fact, a lot of the time, assessors will hand you a deliberately flawed sample part just to test your inspection skills. They want to see if you can spot an undersized dimension or taper error and actually report it like a true professional. So, treat every single practice session in the shop as if it's the real, high-stakes exam. Maintain perfect housekeeping, narrate your steps out loud, and never, ever violate PPE rules. The habits and skills you build right now in practice are the exact ones the assessor will be scoring on the big day. You've got the knowledge now. Review your spindle speed computations tonight, double-check those taper-turning setups, and just remember that methodical, calm preparation is your ultimate key to passing the machining NC2 assessment. So the only question I have left for you is, are you ready to get out there and get to work?